Okay, so we've looked at, I suppose, the future values and that idea of a future value for an amount of money, and then constructing that in terms of a series. If I'm expecting regular payments to be made monthly, or regular installments to be made and to sit in my account and to accrue interest or to increase in value. What we want to look at now is kind of the reverse of that, where maybe I have a certain amount of money in a future time and I want to know what that money is worth now. And I suppose where that kind of comes from is that idea that if I have, say, €500 now, obviously that is worth €500, but we should, I suppose, hopefully have some idea that €500 in 2 years time would not necessarily be worth €500 now, or the €500 that I have now could be worth more in a few years time. And I suppose that's the other kind of flip side of the coin there. So what we're going to be looking at is taking an amount such as our €500, for example, and let's say in 3 years time somebody's going to give me €500. I want to know what is the value of that money now. If I compare it to the money I have now, what is its value? Because obviously what I have now is similarly going to presumably maybe increase in value. And with this, we're looking at present values. Okay, so with the other ones were more future. Here we're looking at more present values. So we pick an amount of money in the future and pull it back a certain length of time. And with that, I suppose we can set up a similar sort of series here by pulling back installments that are made across certain months or years or whatever it is. So if I say I'm going to have a pension where I'm going to get 10,000 every month, for argument's sake, then what I'd be looking at is I would be saying, well, the 10,000 I'm going to get now, when I retire, I need to pull that back however many years. And then the 10,000 the next month needs to come back. It's nearly the same amount, but one more month, and so on and so forth, until essentially I've kind of run out the length of time that I'm considering here. So it's all about kind of pulling it back until now, pulling it back through however many months that it's been there, or that it's been since now, and kind of pulling back its value so we can find essentially like an equivalent value now. Okay, kind of, you're basically accounting for the fact that it will have increased, that the money will have increased in value or wouldn't be worth as much in current value. So suppose that you receive annual payments of 10,000 per annum for a period of 10 years. What is the present value of this stream of payments if the first payment will be made in 4 years' time? Okay, so let's say we are now, then this is 1 year's time, this is 2 years' time, this is 3 years' time, and this is 4 years' time. So we are going back 4 years. Okay, so this payment of 10,000 that I've made here in 4 years' time needs to come back 4 whole years. If I then go to the next payment of 10,000 that was made the next year, it has an extra year to go. So it has 5 years to consider, and so on and so forth for all 10 years that I'm looking at here. Okay, and we're pulling them all back those lengths of time. Okay, so let's kind of set up this sequence here. So as we said, the first 10,000 needs to come back 4 years at an interest rate of 5%. Sorry, I've said 4% there. I got carried away with my fours. 5% for 4 years. And again, that's just using that formula we had above, which is in your formula and tables book. It's the formula for a present value. Okay, to that, I'm going to add the payment that was made in 5 years' time. Okay, and work that one out. Then we have the 10,000 that was made in, let me see, let's do 10 years' time. $11 years' time. Okay, and so on and so forth. Okay, and so on and so forth. Okay, considering how many payments I'm going to have, we have the one for 4 years, 5 years, 6, 7, 8. So that's the first 5. We have the 9th, we have the 10th, we have the 11th, 12th, 13th. Okay, so there's 13 years essentially to be pulled back here. Okay, so there's 13 years nearly that we have to pull back here. So my last payment, 10,000 for 1.05 for 13 at the end there. Okay, but there's 10 terms to be considered. So in terms of setting up our sequence here, the first term is my 10,000 times 1.05 but being brought back 4 years. The ratio that's happening here is that I'm multiplying by 1.01 over 1.05. And we can see that in the denominator, the fact that the powers are increasing suggests that that ratio is multiplying by a fraction there. Okay, n here is 10 because it's 10 years or 10 payments to be made. So let's look at S10 here. That's 10,000 over 1.05 to the power of 4. 1 minus 1 over 1.05, again to the power of 10 now, over 1 minus 1.05. Okay, as we said with the last type of question as well, we maybe avoid filling in any decimals or kind of working out any decimal parts here until as late as possible, to just avoid any possible error in rounding. Usually is kind of the most common one here. So let's put this to the power of 10 as well, and 1 minus 1 over 1.05, and that is 66703. 66703.249. Okay, so about 25. Okay, 66703.25. Okay, so let's look at an exam question or two here. We'll see how many we get through. So I did kind of say there is one style that maybe is a bit more preferred, and it is kind of the present value idea has been a bit more favored. So we'll look at Acme Confectionery has an employee pension plan. For an employee who qualifies for the full pension, Acme Confectionery will pay a sum of 20,000 on the day of retirement. It will then pay a sum on the same date each subsequent year for the next 25 years. Each year the employee is paid a sum that is 1% more than the amount paid in the previous year. Okay, so there's an extra layer to this one, as if it wasn't tricky enough. There's an extra layer to be considered. Each year the employee, so what sum of money must the company have set aside on the day of retirement in order to fund this pension? So the key thing that I can see there straight away is on the day of retirement. So the company here is there at the day of retirement saying, what do we need to have ready to go? So the first thing I would look at is on that day, on the day of retirement, you are due a payment of 20,000. Okay, without a doubt, they've said they pay 20,000 on the day of retirement. You are due that the very first day. The next payment you are going to get is yearly for 25 years. Okay, for 25 years total. So let's put this together. So you're going to get 25 more payments essentially. Yeah, you're going to get 25 more payments. So we're getting 20,000. That 20,000 that I get next year needs to only come back 1 year to work out its value now. So that's 1.05 to the power of 1. However, they have an extra layer in this question where they've said the employee is paid 1% more. So I'm not just paid 20,000, that 20,000 is also increased by 1%. So instead of me getting 20,000, I'm actually getting, I don't know why I'm working this out, 20,200. Okay, so that's what I'm getting there. And then I need to bring that value back to the present day. And when we go to the next year, then we would increase that again, 20,402, and I will bring that back 2 years. So we can look at how that kind of increases here over 1.0. We're doing 1.05 here. 1.024. This is 1.024 to the power of 2, but also 1.01 to the power of 2, and so on and so forth. Okay, so the powers are matching up there. So they've said on the day of retirement and then for the subsequent next 25 years. So I'm going up as far there as 25 and 1.01 for 25. Okay, so that 20,000 at the start and the subsequent or next 25 years is what I'm getting here. And there's loads of extra kind of layers happening on to what's happening here. So let's look at lining all of this up in terms of a series here. The first value there is 20,000. The common ratio is the one I would watch out for here, because the ratio actually is not going to be just the denominator, but there's also an element on the numerator of our fraction as well. because we actually have that increasing on the top and the part on the bottom to consider. And then in terms of n here, we actually have 26 terms because we got the 20,000 at the start, and then we get the next 25 years after that payment as well. So let's set this up. S26, 20,000, 1 minus 1.01 over 1.024 for 26 payments over 1 minus 1.01 over 1.024. Okay, and I'm just going to grab the answer for this one, 44013240. So in order to sustain that for you, this company would have to have 440,000 euro set aside to be able to pay you that amount for the next 25 years following your retirement. Okay, or 26 payments total of 20,000. Okay, we'll just kind of quickly fly through one more example here, I suppose, or one more exam question. So Porg is 25 years old and is planning for his pension. He intends to retire in 40 years' time when he is 65. First, he calculates how much he wants to have in his pension fund when he retires. Then he calculates how much he needs to invest in order to achieve this. He assumes that in the long run, money can be invested at an inflation-adjusted annual rate of 3%. Your answers throughout the question should be therefore based on a 3% annual growth rate. Okay, so that makes sense. I suppose that's the main takeaway from reading that there for the moment. Anyway, write down the present value of a future payment of 20,000 in 1 year's time. So we know our little formula for this. Present value future payment 1 plus I to the power of t. So present value of 20,000 at a rate of 3% in 1 year's time. And we can work that out fairly easily. Just 1.03. Present value of 19,417.48. Okay, so that idea that whatever, this 19,000 will increase in value to be worth 20,000 in 1 year's time. The present value of a future payment of 20,000 in t years' time, well, same idea here, except we now change the 1 there to just be a t, leaving a general case here. Okay, so I'm feeling that they're setting me up to set up a series. Porg wants to have a fund that could, from the date of his retirement, give him a payment of 20,000 at the start of each year for 25 years. Show how to use the sum of a geometric series to calculate the value on the date of retirement of the fund required. So again, we're looking at on the date of retirement, the fund that he would need. Okay, so again, the first 20,000 he gets on the day of retirement. The next 20,000 that he gets has a current value of just 1.03, or it needs to be brought back just 1 year. The next payment after that needs to be brought back 2 years, until the last payment, and we're only getting it for 25 years total, so the last payment is being brought back 24 years. Okay, it's being brought back 24, or in terms of the interest, I suppose it's 24 there. Okay, and the idea there, I suppose, that you get it at the start of the 25th year, so it hasn't sat in the account for 25 years, really, is, I suppose, where you're kind of coming from with that one. So just making sure that our terms add up to 25, and generally, if you have a term without interest, your powers probably will be 1 less than the total number of powers there, with the exception, I suppose, of the one we just had. So let's see, first term, 20,000, common ratio 1 over 1.03, n being 25 here, because it is 25 terms, S25, 20,000 times 1 minus 1 over 1.03 to the power of 25, all over 1 minus 1 over 1.03, and that gives me a value of 358,710.84. Okay, Porg then plans to invest a fixed amount of money every month in order to generate this fund calculated in part C. His retirement is 480 months away. Find correct of 4 significant figures. The rate of interest per month that would, if paid and compounded monthly, be equivalent to an annual rate of 3%. So we've got some practice on this one. 1.03 to the power of 1 is equal to 1 plus m to the power of 12. M is the 12th root of 1.03 minus 1, which makes m 0.0024663. They asked for a rate, so I should convert this to a percentage, so 0.24663%. Write down in terms of n and p the value on the retirement date of a payment p made n months before the retirement date. Since it's before the retirement date, but I want to know what it's worth at the retirement date, I am looking for the future value of this payment that was made. So I want the future value of a payment P at an interest rate of 0.0246663 n months beforehand. Porg's making 480 equal monthly payments of P from now until his retirement. What value will give the fund he requires? So we're getting a nice tie back here now to the future value ones. So he does 480 monthly payments of this. So if we kind of rewrite it this way, his most recent payment that he made will sit in the account for 1 month. Okay, it will sit in the account for 1 month. So it's made at the start of that month and it sits in the account for 1 month there, up to the very first payment that he made, which is now sat in his account for all of those months, the 480 months. So let's set up our formula here as before. Common ratio of 1.002466, n being 25, or where am I going with 25? 480, much bigger, 480 P times 1.002466, 1 minus 1.002466 to the power of 480, all over 1 minus 1.002466. And let's work out what that sum would give me. It gives me an overall answer here of, excuse me. I'm looking for him to get a certain fund. So we, of course, we need him to have €358,710.84. So we need this to be equal to that value, €358,710.84. Okay, so we have a little bit of rearranging nearly to do in this one. Okay, so we'll just take this out to the side. I'm just going to kind of rearrange it here on the fly, I suppose. 385,710.84. That's going to be multiplied by minus 0.002466 all over 1.002466 and 1 minus 1.002466, 480. Okay, and that gives me an overall investment of €390.17 there. Okay, and we're going to look at that as partly in our next section here. And then if Porg waits 10 years before starting his pension investments, how much will he then have to pay each month in order to generate the same pension fund? Okay, so if he waits 10 years, he does have 480 months now, but if he waits 10 years, that is taking off 120 months, which means he only has 360 payments. So we would set up the formula exactly the same with 360 payments, filling all of that in. So the only thing that's going to change here is the overall power, okay, on this part here, 2466, 360. Okay, and we get the overall answer that the fund needs to be 618.35. Okay, so we estimate to pay not double, but definitely at least nearly two something more, nearly 3 more. Okay, overall takeaway here hopefully should be that we're identifying the difference between when we're asked to pull the value back and when we're asked to look into the future for a value, and it all depends on where we are, okay, relative to the amount of money or when the money was introduced. So if the money is being paid in the future and I'm not in the future now, I'm in the past, I'm pulling its value back. If I'm in the present but the money, I want to know its value in the future, then I'm looking at a future value. Okay, so that, I suppose, wraps up really in terms of the geometric series part. We just have then another formula which is closely related to this idea here.